Hi, and welcome to Unit 21. Unit 21 deals with the dual nature of light and matter in general. Both of them actually have that duality. So let me talk about the objectives in here. So we're going to describe how light sometimes behave like waves and sometimes behave like particles. Historically, it started that light actually was was accepted to be behaving more like a particle than anything else through the phenomenon of reflection. Like when you stand in front of your mirror, there is a reflection of your face because light is hitting the mirror and bouncing back, and that's where you see yourself in the mirror. Or through lenses, for example, or water or something, when light goes through the other side to the medium, it refracts. So the explanation for it is that light must be a particle traveling with different speed through different media depending on their thickness. Also, it can be as a wave because light exhibits wave phenomena. Like, for example, interference. Okay, that's only waves that can do that. Okay, then recall the speed of light. Historically, the speed of light was, now we know it's 300,000 kilometers per second. And so the first time it was measured based on the observation of the moon Io of Jupiter and how much delay it does 6 months apart, basically, because the position of the Earth shifts 6 months to the other side of the Sun, whereas Io takes only 12 days to go around Jupiter, 2 days to go around Jupiter, and Jupiter takes about 12 years to go around the Sun. So it was an opportunity for us to estimate it's actually Romer is the one who came up with that first estimate. Then Fizeau improved on that number with a different experiment. And at the end, we have the current value nowadays of 300,000 kilometers per second. And the fact that now we know actually it's the electric field and the magnetic field disturbances that travel, and that's what light is, really. Okay, it's these waves of electric field and magnetic field. So that's the nature of light. Define and explain the inverse square law. Basically, what that is that if you shine a light, for example, and you're very close from it, it looks bright. As you move further and further back, it dims. The further you are, it dims. At some point, you will probably, if you move a mile away from something, it's not going to be seen. And that's because light spreads throughout a big sphere, and that sphere is proportional to the square of the distance, the radius of that sphere, and that's why the light dims as you move away from it. Okay, take two light sources, for example, two candles. Okay, put one in here and one in there, and both of them are the same type, same thing. The closer one will appear brighter than the further one from you. And then describe how light interacts with matter, basically. So let's talk about it. So I mentioned the speed of light, 300,000 kilometers per second. Okay, and this seems to be universal, by the way, to the point that it's a constant. The universal constant is the maximum speed. No matter can move faster than the speed of light. And I emphasize the word matter in here because light itself is not matter. It's matter of fields, okay? And that's not material. It doesn't have mass, okay? But light is also energy that is being radiated, carries with it energy. And it can behave as a particle, it can behave as a wave. So it has a dual nature. Those are two complete opposite natures. So they should not really exist. They're mutually exclusive. But yet, for the case of light, light does both, okay? Which is kind of contradictory to some extent. So here is the case. You have a small disturbance, and that disturbance basically creates an electric field, which generates a magnetic field, which creates an electric field, which generates a magnetic field, and that becomes self-sustained, and it travels all the way from the source to the point where you want to collect it. Okay. So what is waving in this case is the electric field and the magnetic field. Okay. And as I said before, this exhibits interference phenomena. Basically, you could have two waves with opposite phases canceling one another. And if they have the same phase, they amplify one another. So basically, that's what interference is. So if you go on the lake, for example, and you drop a rock, the surface of the lake, there will be waves, okay, disturbances that travel. Those waves are characterized by peaks and troughs, and in between there is nothing. Okay, so that's how waves are. And if two waves come in with opposite phases, they cancel. If two waves come in with similar phases, they actually become bigger. Okay, and that's what waves are. So light is a wave in a sense. Okay, there is no argument about it because you can prove it through experiments and you can see it behaving as a wave. Also, light behaves as a particle. If you have solar panels on your house, that's the particle nature of light that really causes the solar panels to give you electricity at home. When light particles hit the surface of the material that is the one that you have on the solar roof, on the solar panel, it ejects, it collides with an electron and frees an electron. Okay, so there is a collision of two particles. It's like you're playing billiards, basically. White ball hitting the eighth ball, for example, and they collide. One of them moves in the opposite, in the different direction, and that's the case in this case. So this cannot be explained by waves. Waves don't do that. If a wave comes in, it will just go through. So that's a good example of that. Okay. So and Einstein gave them a name: photons. Photo means light. Ons means particle. On means a particle in general. So it's the particles of light. That's exactly what that means. So it has a dual nature. Depending on what you're doing, it can behave as a wave for you. And if you're doing something else, it behaves as a particle. By the way, the photoelectric effect, which has to do with the solar panels, is not the only one for where light behaves as a particle. There are all kinds of them. Okay. So as light leaves the source, this is how much light is coming immediately from the source. But then it starts to spread through a big sphere, okay, in all directions. You're here on Earth looking for the light. You're not getting this one or the others. You're just getting a fraction of it, okay? If the Earth was closer, let's say, for example, here, it would get all of these three, okay? So that's basically how you understand the inverse square law, because the light source emanates from a source and starts to spread through a big sphere. So as it does, the portion where you're supposed to be having it is going to be part of a bigger portion that's spread throughout a big sphere. So it drops like the square of the distance. 4 pi d squared in this case is the size of the sphere, the area of the sphere surrounding the source, in this case the sun, at a distance d, which is the radius of that sphere. Okay. So that's the inverse square law. As I mentioned before, take two candles, for example, or two light bulbs, or two 40-watt light bulbs, for example, and one of them is up close to you and the other one is moved further away. Well, the one that is away is going to appear dimmer anyway because its light spread over a bigger area than the one that is closer from you. Okay, that works for any signal, by the way. Even your cell phone, if you're close from the tower, you will have 4 bars. If you move further away from the tower, the number of bars starts to drop. Same thing with sound. If you're closer from the sound source, you're going to hear it at a high volume. As you move back and back, the volume starts to dim because sound also is a wave, okay, and it propagates through a similar phenomenon, okay. The nature of matter, basically, that's also another thing. And here, matter is made up of, atoms are made up of a nucleus that's positively charged and electrons that are spread throughout the nucleus in some sort of a cloud structure, okay? And this is a simplistic version of the atom because this is not necessarily the orbital distribution of the electrons around the nucleus. They could have all kinds of shapes, but this is the simplest version of that. So basically, the lowest energy. So they have to stay in orbitals. They have to stay in different energy levels. Okay, for the stability of the atom. The rules for that come from quantum mechanics, so that you know. Okay, and for the case of hydrogen, the lowest energy level, where the electron is sitting at home and basically minding its own business, called the ground state, sits at 0.05 some change in here, 0.053 nanometers. So it's really a very, 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 very small distance, okay, compared to the wavelength of light. The shortest wavelength, which is 400 nanometers, this distance is ridiculously small, okay? Compare 400 to 0.05. So the size of the first orbit of the hydrogen atom, which is the lowest energy level, which is the ground state where you would find the electron anyway, is very, very small distance, very close from the nucleus. Okay, the nucleus is extremely small, even smaller than that. It's about 100,000 times smaller than this number. Okay, so you see how the sizes are. Okay, and then the first excited state in this case, which is the 1s state, is sitting at 0.2 nanometers. You're looking at about 4 times further away than this one, okay? And it's actually 4 times, because there is something has to do with the number squared, okay? So the first one is 1, the second one is 2, you square 2 is 4 times. The next one is 3, 3 squared is going to be 9, okay? 9 times, and so on and so forth, okay? 9 times this number, okay? So that's basically the different energy levels. Every atom would want to be in its ground state. It doesn't want to be somewhere else. So if you have 2 electrons, for the case of helium, for example, both electrons will be actually sitting in here. One of them with a spin up, the other one is spin down. Okay. If you have had chemistry, you know exactly what I'm talking about. Okay. For the case of beryllium, the third element in the periodic table, you have 3 electrons. So in this case, this level is full. You can't put any more electrons. The next electron must go in here, and so on and so forth. Okay. So that's how atoms are. They are all neutral. The number of electrons is equal to the number of protons inside the nucleus, and everybody's happy. Okay. And except that there are some neutrons to help stabilize the nucleus, because the nucleus is not just made up of protons. Protons are positively charged. So if you have 2 protons next to one another, in the case of helium, they would want to repel each other, although they have a strong force in this case called the nuclear force that hold them together, but it's not really stable. So you need really 2 neutrons to help put things, keep them stable. Okay. So that's the whole chemistry has to do with the number of electrons, basically how electrons behave, so that you know. Okay. The way light is absorbed by particles, by matter in general, is it has to have the right wavelength, the correct frequency. Anything other than that is going to sail through. The frequency has to correspond to a specific transition between 2 different energy levels, between n equals to 1 and n equals to 2, or 1 to 3, or 1 to 4. This must have a lot of energy if you were to take 1 all the way to 4, because it's a big gap in terms of energy. Or between 2 and 3, or 2 and 4, and more. 2 and 5, 2 and 6, to all the way there, whatever you want to. 3 and 4, which doesn't require a lot of energy, by the way. 3 and 5, and so on and so forth. Okay? So that's why you have to have the right amount of energy. And if you do have it as a wave, as light, then that light is absorbed. And then the electron that was sitting in this case in energy level 2 could jump and find itself in energy level number 3. This is not really a physical jump, so that you understand. It just happens immediately. It takes this electron, it's in here, now it finds itself here. It's not like a physical migration like you might imagine, okay? So that's how the process works. So in this case, light is absorbed. And if we were to do a spectrum of this one, that's called an absorption spectrum. We will see all this light that passed through, except we're missing some lines that did get absorbed. So that material has specific pattern, in this case, characteristic of this wavelength, okay, that have been absorbed. In a similar tone, we could have an emission. As I said before, atoms really want to be in the ground state. So if they find themselves, for example, excited is when they are not in the ground state, then they want to go back to the ground state. And they can be excited either by absorbing photons, like I was describing earlier, or by getting some energy somehow, like heat, for example, or something like that. Now they're excited. They're not where they're supposed to be. So they emit that excess energy through radiation. So in this case, if the ground state is 2 for this atom, and this electron found itself to be at level 3 by absorbing the same wavelength, for example, or by absorbing much more energy, like going all the way to level 4, and then going down to 3. Now it's sitting in a 3, but it's still not the ground state either. So it wants to come back to level 2, and it's going to emit that same wavelength in this case, okay? It could be heat up. So that's an emission spectrum. So if I'm running an emission spectrum, for example, I put my gas inside under voltage, so that excites it. So the voltage will cause the atoms in there to not to be in the ground state. Then all automatically they want to go back to their ground state by emitting light, characteristic of that gas. Okay, so I will see then in this case an empty spectrum with the exception only some lines indicating that I am getting these lines from that element. We're going to talk more about the spectroscopy down the road. Thank you.